All right, so this is going to be about logic gates and circuits. Okay, so we can think of logic gates like this. So true equals 1, which is circuit is on. This is easy if you come from software engineering. Boolean, like primitive values, can be thought of as just 1. And then same thing with false. That can be thought of as 0. And the circuit is off. So false equals 0 equals the circuit is off. So 1 is circuit is on, 0 circuit is off. And then the wires in the circuit are in states on or off. Okay, so circuits are governed by gates. The gates take on/off as input, and the output of a gate is on/off. So these circuits, these gates, that's what they receive as input, on or off, and their output is on or off. And the gates are the operators. So and, or, exclusive or, NAND, not. And this idea boils down to the fact that Boolean logic can be represented by electrical signals governed by the gates that are Boolean operators. So these operators govern, these are the gates, and they govern the circuit. So here's an example of one. And this is important because gates are the building blocks for creating circuits that evaluate Boolean expressions. So think of a whole Boolean expression, like a whole bunch of these not and not A and B or C. Think if there was just a whole bunch of them. This expression can be evaluated using these circuits. And if you look at the picture here, A and B are those two lines. Those wires are going into the gate. It's a square and half circle combined. Ignore the line, the vertical line going down the middle. I'll demonstrate this better later on, but that overall shape, the half rectangle, half circle, that is an AND gate, an AND operator. So A and B. And you can see that in the expression written in the top left, A and B. So you can think of that part of the circuit, that gate is A and B. And then we're going from left to right. So continuing with that gate, it goes into another gate, which is like kind of like an arrowhead. It's like it looks like an arrowhead or shark tooth. So that is going into an OR operator. That shark tooth arrowhead shape, that's an OR operator, an OR gate. So the output of A and B is going into that operator, that gate, the OR gate. And it's also has C. So it's C or the output of A and B. And then you continue going left to right. That triangle with a circle at the end of it, that is a NOT operator. So you can kind of see how that NOT operator is the outermost operator on the written expression. Okay, so now you can look at multiple input gates. This right here is an AND operator right here. And you can see on the written expression A and this caret is an AND operator. B, that's another variable, another AND operator, and C. So this whole gate is A and B and C, and the output is going to be whatever these, depending on what A is, or depending on what A, B, and C are. And then this is the OR operator, this shark tooth right here. And you can see it's represented right here with that upside down caret, OR. So it's A, OR, B, or C. And the output of this gate is D. So let's see if we have you can see a truth table like this. So A and B equals C. When they're both false, it's false. We went over this in a previous video. When they're both true, it's true. If only one is true, then it's false. And then same thing with, or not the same thing, but continuing with the OR operator. If they're both false, then it's false. If one is true, it's true. Or if both are true, it's true. So you can see how you can chain these gates together and to create a circuit to evaluate this this Boolean expression. So A and B and C, that's right here. We got D and E, that's this gate right here, and then not F. So you can see how that all of this goes into an OR gate. So the output of this, or the output of this, or the output of this. And that's what G equals. And we can see that written here. G equals A and B and C, or D and E, or not F. Not F, D and E, A and B and C. Here's another one. A and B and C equals D. A and B, or A or B or C equals D. And you can represent these. These can be represented in other ways. So A and B, the output of that, and C, these are equivalent right here. They're just written differently. You have A or B, the output of that goes into OR, another OR gate. So C or the output of A or B equals D. Okay, here's some more equivalent circuits. This is A and B. This can be rewritten using not operators. So maybe it's better to look at it written first. So this is A and B at the bottom right here. Now we can change this to not A, or we can, excuse me, not A and not B. And then you can do it, also write it this way, not A or not B. So this can be expressed with gates and operators right here. So not A, the output of that, or the output of not B, and we can see that here, not A or not B. And then this one right here is a not operator on everything before it, and that's this one right here. And these are all the same. It has the same truth table. All right, here's another one. A or B equals C. You can see right here. And this can be expressed using not operators. So looking at the written expression, not A or not B. And you can do not A and not B. And you can see that in the gates using the operators. So not A is the input going into this AND operator. Not B is the input going into that same AND operator. And we can see that right here. Not A and not B. Not A and not B. And all of that output goes into this not operator, which is right here. And that equals C. So the same thing. And we'll stop right there.